Mars feels like the obvious future. But if the real question is, which planet could change planetary science more? The answer may be Venus. It is closer, more extreme, and may hold some of the biggest unanswered questions about climate collapse, habitability, and how Earth-sized worlds fail. So this is not just Mars versus Venus. It is whether we have been focusing on the easier story instead of the more important planet. Venus is not just hot. Venus is the most extreme failed Earth in the solar system. People hear that Venus is hot and treat it like a more severe desert, or a planet with terrible weather. That is much too weak. The surface of Venus is above 900 degrees Fahrenheit, about 482 degrees Celsius. The pressure at the surface is around 90 times higher than at sea level on Earth. That is not a rough environment in the normal sense. That is an environment where the basic conditions destroy standard assumptions about survival. This is not Earth with a few bad settings. This is a rocky planet close to Earth in size and broad chemistry that took a very different path and became the hottest planet in the solar system. That is why Venus matters so much. It is not just a hostile world, it is evidence. It shows that a planet with some major similarities to Earth can end up somewhere completely different. So Venus is not just a strange side topic in planetary science. It is one of the strongest warnings in the solar system. Something happened there that pushed an Earth-sized world into an extreme state. And we still do not fully know the full story of how that happened. Then the obvious response comes in. If Venus is that important, why is Mars still the centre of so much attention? Because Mars earned that position. Mars absolutely deserves its reputation. It is where the exploration momentum is. It is where mission heritage is strong. It is where space agencies already know how to operate with some confidence. NASA says it currently has 5 active missions at Mars. Mars is the only planet we know that is inhabited entirely by robots. That matters because it shows just how far the Mars program has advanced. We have orbiters, surface missions, relay systems, landing experience, and a growing international framework built around Mars. That level of continuity changes everything. Every mission helps the next one. You get better maps, better landing data, better hazard knowledge, better weather understanding, better communications, and better science targets. Mars is no longer just a place we visit now and then. It is a planet where exploration has become structured and repeatable. There is real infrastructure there, even if it is robotic and limited. But that creates a twist that is easy to miss. Mars is the world where exploration is stable. Venus is the world where the science could still be disruptive on a much larger scale. That is the key difference. Mars keeps producing valuable discoveries, and it will keep doing that. But a successful decade at Venus could change several areas of science at once. It could change how we think about climate evolution, volcanism, atmospheric history, habitability, and even rocky exoplanets around other stars. Mars is powerful because it is mature. Venus is powerful because it still has the ability to seriously surprise us. So why does this question matter right now instead of 10 years ago or 20 years ago? Because Venus is no longer sitting on the sidelines. That part is changing fast. NASA's DAVINCI mission is currently listed with a tentative 2030 launch. VERITAS is listed no earlier than 2031. ESA's EnVision is planned for November 2031. That means the 2030s are shaping up to be the first truly serious return to Venus science in decades. And that matters because a planet can stay in the background for a long time, then suddenly become central once the mission pipeline becomes real. That is exactly what may be happening with Venus now. So this is no longer just a provocative question for a documentary title. It is becoming a live strategic question. If multiple major missions go to Venus in the same decade, then Venus stops being the forgotten inner planet and starts becoming one of the main places where planetary science gets rewritten. And that brings you to the real tension running through this entire video. If your goal is human footprints as soon as possible, Mars is still the stronger option. Mars is harsh, but it is a kind of harsh that engineers can at least approach step by step. If your goal is the biggest unanswered science jackpot in the inner solar system, Venus may be the better target. That is why this is not really a simple Mars or Venus argument. It is a question about what kind of future we are optimizing for. Have we been choosing Mars because it is truly the most important target for the next phase of planetary science? Or have we been choosing it because it feels more survivable, more familiar, and easier to build a story around? That is where Venus becomes uncomfortable. Mars gives you a frontier you can picture. Venus gives you a problem you cannot ignore. Mars feels like the place where humans may one day try to live. Venus feels like the place that may explain why Earth stayed habitable while another Earth-sized world did not. And that is why this debate matters more than it first appears. It is not just about where spacecraft should go next, it is about what kind of answers we want first. Do we want the planet that fits our expansion story better? Or the planet that may tell us something more serious about climate, planetary failure, and the narrow conditions that let a world remain stable for billions of years? Because once you frame it that way, Mars still looks like the practical favourite. But Venus starts to look like the more dangerous truth. And that means the next question gets even harder. If Venus and Earth are so close in size, why do they end up so completely different? How can two planets that start so close end up this far apart? That is the part that makes Venus hard to ignore. Venus and Earth are close in size. They are close in density. That is why people call Venus Earth's twin. And that nickname sounds harmless until you really stop and think about what it means. You're not comparing Earth to some tiny airless rock with no atmosphere and no real complexity. You're not comparing it to a giant gas planet that was always going to be different. You're comparing Earth to another rocky world that started with many of the same basic advantages. Similar size, similar bulk composition, similar place in the inner solar system. And somehow that world ended up becoming one of the most hostile planets anywhere near us. That is why Venus is so scientifically brutal. If Venus were obviously different from the beginning, it would be easier to explain away, but it was not obviously different in the ways that matter most at first glance. That means every fact about Venus hits harder, because every fact forces you to ask the same question again. How did a planet that should have been at least somewhat ordinary become this extreme? And that is why Venus is not just interesting, it is unsettling. It tells you that having the right starting conditions does not guarantee anything. A rocky planet can begin in a category that looks familiar and still end up completely outside the range of what you would call friendly, stable, or even remotely Earth-like. So what actually went wrong there? Did Venus just get a little hotter over time? No, Venus did not just warm up, Venus ran away. This is where a lot of people get the basic picture wrong. They think Venus is hotter than Earth because it is closer to the Sun, and that is part of the story, but only part. If distance from the Sun were the whole answer, Mercury should be the hottest planet, because Mercury is much closer to the Sun than Venus is. But Mercury is not the hottest planet, Venus is. And that one fact should stop you immediately because it tells you something bigger than a temperature ranking. It tells you that distance alone does not decide the fate of a world. Atmospheres decide worlds. Venus has a massive atmosphere made mostly of carbon dioxide. That atmosphere traps heat so efficiently that the surface becomes even hotter than Mercury's, despite Mercury being much nearer to the Sun. That is not a small detail. That is the whole lesson. Venus shows you what happens when greenhouse heating scales up to the level of planetary destiny. The atmosphere does not just make Venus warmer. It dominates the entire surface environment. And once you understand that, Venus becomes much more than a hot planet. It becomes one of the most important examples we have for how rocky planets succeed or fail. If a planet can start out looking broadly Earth-like and then end up in a runaway greenhouse state, then habitability is not something you can assume from size alone or even location alone. A planet can be in the right general category and still go very wrong. That matters for understanding Earth, and it matters even more when you think about exoplanets. Because once you know Venus exists, you stop treating Earth size as a comforting label, you start asking harder questions. What is in the atmosphere? How thick is it? How did it evolve? Did the planet keep water? Did it lose it? Did the climate stabilize, or did it cross some point where it could not come back? Then the obvious counterpoint appears. If Venus is the example of too much atmosphere, what is Mars the example of? The opposite failure. Mars is cold, dry, and thin-aired. NASA describes it as a cold desert world. Its atmosphere is also mostly carbon dioxide. But it is much thinner than Earth's and nowhere near thick enough to trap heat the way Venus does. So if Venus shows you what happens when a rocky planet keeps too much atmosphere and traps too much heat, Mars shows you what happens when a planet loses too much. It loses warmth. It loses pressure. It loses long-term climate stability. It loses the conditions that once may have allowed liquid water to remain more widely present. That is why Venus and Mars matter so much together. They are not just two different planets with two different weather systems. They are two different failure modes for rocky worlds. Venus is what happens when the atmosphere becomes overwhelming. Mars is what happens when the atmosphere becomes too weak to protect the surface and support long-term habitability. And that means Earth is sitting in between two warnings. On one side, a planet that overheated. On the other side, a planet that faded. That is already enough to make Venus important. But then Venus adds another layer that sounds almost fake the first time you hear it. Venus has a day longer than its year. That sounds like a strange piece of trivia, but it matters. Venus takes about 243 Earth days to rotate once. It takes about 225 Earth days to orbit the Sun. So one full rotation takes longer than one trip around the Sun. And Venus also rotates in the opposite direction from most planets. In simple terms, it spins backwards compared with Earth and Mars. Now that may sound like just a weird fact to surprise people with, but it is more than that. Rotation affects how a planet handles sunlight, heat movement, atmospheric circulation, and long-term climate behavior. So when scientists study Venus, they are not only dealing with a thick carbon dioxide atmosphere and extreme surface conditions, they are also dealing with a planet that behaves differently at a deep physical level. Its clouds, winds, and thermal structure are all shaped by conditions that do not match Earth or Mars. That is why Venus keeps becoming harder instead of simpler the more closely you look at it. The chemistry is extreme, the surface is extreme, the atmosphere is extreme, the rotation is unusual. Even basic comparisons keep breaking your intuition. So what is the real comparison here? Is it just about which planet is nicer? Not even close. The real comparison is which planetary failure mode should worry you more. Mars is the story of loss. Loss of atmosphere, loss of water, loss of long-term stability. Mars looks like a planet that could not hold on to what made it more habitable in the past. Venus is the story of excess. Too much atmosphere, too much heat trapping, too much pressure, too much divergence from the path Earth followed. Venus looks like a planet where climate and atmosphere did not just shift a little. They pushed the whole world into a different state. And when you put those two planets next to each other, Earth stops looking like the default. Earth starts looking like the narrow middle ground. That is why the Venus versus Mars question is really a question about Earth. What keeps a rocky planet balanced for billions of years? How much atmosphere is too much? How little is too little? How stable is liquid water over geologic time? How easy is it for a planet to cross a line and not recover? Because if Venus and Mars are both common outcomes for rocky planets, then Earth may not be the standard case at all. Earth may be the rare case that stayed in the narrow zone between overheating and collapse, and that is what makes Venus so dangerous as an idea. It forces you to stop asking which planet looks more comfortable from far away, and start asking which one tells you the more serious truth. Mars tells you how a world can die by losing too much. Venus tells you how a world can become unlivable by keeping too much. Between them, they define the edges of habitability. And once you see that, another easy assumption starts to fall apart. People hear that Venus is closer to Earth and think that should make it easier to prioritize. But closer does not mean easier when the destination itself is built to punish every mistake. If Venus is closer, why are we not already treating it like the easier target? That is where a lot of people get misled very fast. Venus is Earth's closest planetary neighbour, and that sounds like it should settle the argument immediately. If one planet is closer, then surely it should be simpler to reach, simpler to plan for, and maybe even simpler to prioritise. But space missions do not work like normal travel. You are not driving in a straight line. You are dealing with orbital mechanics, launch windows, approach speed, heat exposure, communication geometry, power management, and what kind of environment is waiting for you when you arrive. So closer is true, but it is also incomplete in exactly the way that matters most. That is the distance trap. A planet can be closer in raw space terms and still be harder in the ways that actually define mission success. And this is where Mars has a major advantage that is easy to underestimate. Mars already has a repeatable travel rhythm. That matters more than people think. When Perseverance launched in July 2020 and reached Mars in February 2021, that 7-month cruise fit into a mission pattern agencies already knew how to run. That was not some one-off miracle. It was part of a larger system built over decades. Orbiters, landers, rovers, entry systems, communications relays, navigation methods, surface operations, hazard planning. Mars is not just a place we can get to. Mars is a place we know how to plan for with increasing confidence. And that kind of experience becomes a hidden form of infrastructure. It means the raw distance to Mars matters less than you might think, because the route is familiar. The mission logic is mature. Teams know what questions to ask early. They know what tends to fail. They know how to build timelines, landing profiles, relay support, and surface science plans around a destination that has been visited many times before. Mars is farther, but Mars fits a practiced operational pattern. So then the obvious question comes up. If Mars has the advantage of routine, does Venus have any travel advantage at all? Yes, and this is where Venus becomes tricky. Venus gives you real atmospheric advantages and serious environmental penalties at the same time. Its atmosphere is extremely thick. That creates opportunities Mars cannot match in the same way. A thick atmosphere can help with aerobraking. It can help with entry and descent concepts. It can support studies of aerocapture in ways that are much harder at Mars because Mars has such a thin atmosphere. In other words, Venus can help a spacecraft slow down. That is not a minor detail. Slowing down in space is expensive. If a planet's atmosphere can do some of that work for you, that is a real engineering asset. Magellan is a great example of this. It used atmospheric drag at Venus to reshape its orbit. So Venus is not a place where the atmosphere is only a problem. Sometimes the atmosphere is also part of the solution, but the same atmosphere that helps you arrive is also the thing that makes long-term survival so brutal. That is the contradiction. Venus can assist with approach and orbital shaping, but once you go deeper, the atmosphere turns into a severe hazard. Pressure rises fast, temperatures rise fast. The chemistry becomes corrosive. The closer you get to the surface, the more the environment starts punishing every assumption built into normal spacecraft design. So Venus gives and takes away at the same time. It can make certain parts of arrival easier, then make the actual mission much harder. That is why closer is such a dangerous simplification. Getting near Venus is not the same thing as operating at Venus. And once you realize that, another important point comes into focus. Venus is already doing a lot of work in deep space exploration, just not in the way most people notice. A lot of major missions have used Venus even when Venus was not the main destination. Parker Solar Probe is one of the clearest examples. It used 7 Venus gravity assists to tighten its orbit around the Sun. That means Venus is already a major dynamical tool in the inner solar system. Spacecraft use its gravity to reshape trajectories and reach other goals more efficiently. That is important because it kills a common false idea. Venus is not inaccessible. Spacecraft can absolutely get near Venus. In fact, they do. Venus is part of the operating logic of inner solar system mission design. Engineers already know it can be used as a gravitational asset. So the main barrier is not whether we can approach Venus at all. The barrier is what happens when you decide not just to pass by, but to stay, descend, map, sample, survive, and keep doing science there. That is where the problem changes from navigation to endurance, and that difference matters because people often blend those two things together. They hear that Venus is close and they assume closeness solves the main challenge. But for planetary exploration, the travel distance is only one layer of difficulty. The destination environment may matter much more. A shorter path to a far more hostile place is not automatically the easier mission. In many cases, it is the opposite. So this is the contradiction you have to hold in your head at the same time. Mars is farther away, but once you have built the tools, it is more operationally forgiving. Venus is nearer, but the penalty for mistakes is much harsher. Mars asks for patience and system building. Venus demands survival under conditions that push hardware toward failure very quickly. That is why the distance argument by itself cannot settle the debate. One planet is farther and workable. The other is closer and deeply hostile in ways that break simple intuition. And once you understand that, the whole discussion becomes more serious. The question is no longer just which world is nearer. The question is which kind of difficulty matters more. A longer route to a planet we know how to handle better, or a shorter route to a planet that becomes vicious the moment you try to operate there for real. And that is where the comparison gets sharper. Because talking in general terms is one thing. Looking at what we have actually managed to do at Venus and Mars is another. One planet built continuity. The other built some of the hardest and shortest survival records in the history of spaceflight. If Venus is so important, what have we actually done there? This is where the story gets more interesting because Venus was never ignored because it was useless. In fact, Venus was there at the beginning of interplanetary exploration. One of the biggest early milestones in space history happened because of Venus, not Mars. In 1962, NASA's Mariner 2 flew past Venus and became the first spacecraft to visit another planet. That one fact changes the normal way people think about this topic. The first real success in visiting another planet did not come from a Mars-first future. Venus was one of the first major targets because scientists already understood that it mattered. And for a while, Venus did not look like a side route at all. It looked like one of the main roads into planetary science. It was close, it was mysterious, and it was clearly important. So when people talk now as if Venus has always been the forgotten planet and Mars has always been the main prize, that is not the full story. Early on, Venus was central. It helped open the door to exploring other worlds in the first place. Then the obvious question is, if Venus mattered that much early on, did anyone actually manage to do more than a flyby? Yes, and this is where the story gets much more serious. The Soviets did something that still sounds extreme even now. They landed on Venus. That is not just an impressive line in a history book, that is one of the hardest engineering achievements in planetary exploration. Multiple Soviet Venera probes reached the surface of Venus, and one of them, Venera 13, set the most famous endurance mark by surviving for 127 minutes on the surface. That number matters because it shows both sides of the Venus problem at the same time. On one side, it proves that engineers can push hardware into conditions that look almost impossible. On the other side, it proves how unforgiving Venus really is. Think about the contrast. On Mars, people often talk about mission lifetimes in months and years. On Venus, the most famous surface survival record is counted in minutes. That difference tells you almost everything you need to know about the environments involved. Mars is hard, but missions can keep working. Venus hits you with a level of pressure and heat that turns survival itself into the first objective. The science becomes important, but the first fight is just staying alive long enough to do any science at all. And that is why the Venera missions still matter so much. They were not just historical stunts. They showed that Venus is reachable, landable, and measurable, but only under conditions that make ordinary mission design look weak very quickly. They proved that Venus is not beyond reach. They also proved why so few missions have tried to follow that path all the way to the surface in modern times. But landing and surviving for a short time is one thing. Did we ever get past that and actually learn what Venus looks like as a world? Yes, and this is where one mission changed the whole picture. Magellan turned Venus from a hidden world into a mapped planet. That transformation is easy to underestimate because radar mapping sounds less dramatic than landing in an inferno. But in scientific terms, it was one of the biggest jumps ever made in understanding Venus. Venus is covered by thick clouds, so you cannot just look down at the surface the way you can on Mars. Ordinary visible light imaging is blocked. That means if you want to understand the ground, you need another method. Magellan used radar to map the planet through the clouds, and the result was huge. It mapped 98% of the Venusian surface at roughly 100 to 150 meter resolution. That changed everything. Suddenly, Venus was not just a bright cloud-covered object with terrible conditions underneath. It became a geologic world you could actually study. Magellan revealed volcanic plains, long lava channels, mountain belts, unusual domes, and signs of tectonic deformation. It gave scientists real surface structure to work with, real landforms, real patterns, real clues about how the planet had evolved. That is why Magellan matters so much. It did not just show us Venus. It changed the category Venus belonged to. Before that, Venus still had a strong element of hiddenness. After Magellan, Venus became a mapped planet with a readable geologic story, even if many chapters were still missing. It stopped being a blank sphere and became a world with terrain, structure, and history. So with breakthroughs like Mariner 2, the Venera landers, and Magellan, why did Venus not build the same steady momentum that Mars did? Because Mars got something Venus never really got. Continuity. That is one of the biggest differences in the entire Mars versus Venus story. Mars has had a long overlapping sequence of orbiters, landers and rovers producing a constant stream of new data. It is not one isolated success followed by a long gap. It is a chain. One mission hands useful knowledge to the next. NASA describes Mars exploration as an international fleet maintaining continuous scientific discovery, and that is the right way to think about it. Mars has become an active system, not just a series of disconnected visits. And that kind of continuity builds power over time. It means later missions arrive with better maps, better weather knowledge, better landing zone selection, better communication support, better hazard awareness, better surface context, better science priorities. Every mission benefits from the ones before it, and then adds something new for the ones after it. That is why Mars feels so much more operationally mature. The exploration program there compounds. Venus never got that same runway. It had major moments, important moments, historic moments, but it did not get the same uninterrupted build-out. It did not get the same long chain of overlapping modern missions creating a stable, growing exploration ecosystem. That is not because Venus was less important scientifically. It is because Venus makes continuity much harder to sustain. The environment punishes hardware, limits surface duration, complicates long-term operations, and raises the cost of every major attempt. And that is why the asymmetry matters so much. Mars has been allowed to grow into a living exploration theatre. Venus has remained a place where every return requires reopening problems that Mars missions are now much better at working around. Then the contrast gets even sharper. How far has Mars exploration advanced while Venus has been trying to rebuild momentum? Far enough that we achieved powered flight on Mars before Venus got its modern comeback. That sounds almost backwards when you stop and think about it. Mars has become such a mature exploration environment that NASA tested aviation there. Ingenuity completed 72 flights over nearly 3 years. It covered about 17 kilometers, flew for 128.8 minutes total, and reached an altitude of 24 meters. That is an extraordinary milestone because it means Mars is not just a place where we land and drive. It is now a place where we tested another mode of exploration entirely. That tells you how established Mars has become. We had enough environmental knowledge, enough engineering confidence, and enough operational support to attempt powered flight on another planet. Meanwhile, Venus is still working its way back toward a serious modern mission cadence. That difference is not about scientific value. It is about the fact that Mars, for all its difficulty, gives hardware more room to keep functioning. Venus does not. Venus pushes every system toward its limit much faster. So when you compare what we have actually done, the answer is not simple. Venus gave us some of the boldest achievements in planetary exploration history. First planetary flyby success, surface landings under extreme conditions, global radar mapping through permanent clouds. But Mars built something else that may be even more important in the long run. Continuity. Mars turned exploration into a sustained program. Venus produced historic breakthroughs, but not the same steady operational ladder. And that is exactly why this comparison stays so tense. Venus proved early that it mattered. Mars proved over time that it could support a continuous strategy. One planet gave us some of the hardest wins in space history. The other gave us a platform to keep winning again and again. And once you look at the data coming back now, the next question becomes even more serious. Because Venus may not just be a difficult planet with an important past. It may be geologically active right now. Was Venus always just a dead world hidden under clouds? Or have we been looking at an active planet and not realizing it? For a long time, that was one of the biggest questions about Venus. Scientists already knew Venus had a volcanic past. The surface clearly showed signs of major eruptions, huge lava plains and large-scale resurfacing. But the big uncertainty was whether that was all old history. Maybe Venus had its active phase a very long time ago. Maybe it had some kind of major resurfacing event and then mostly quieted down. Maybe the world under those clouds was dramatic in the past, but mostly inactive now. That question stayed open for decades because we did not have the kind of repeated modern observations that let you watch the surface change in real time. And that matters, because without repeat observations, a planet can look frozen even when it is not. You can map it once, study the shapes, and make educated guesses. But until you compare one high-quality view against another, you cannot easily say whether the planet is still doing anything now. Mars, by comparison, looked much quieter on human timescales. Venus was the bigger unknown, and the strange part is that some of the answers may have been sitting inside old radar data the whole time, waiting for people to go back and look harder. So the question changed from, did Venus have volcanoes, to something much more serious. Is Venus still active now? That question got a major answer when scientists went back to Magellan data and found something that was hard to explain away. In 2023, researchers analysing archival radar images from Magellan found direct evidence of recent volcanic activity on Venus. They identified a volcanic vent that changed shape and became much larger in less than a year between two observations. That is the kind of result that changes the whole tone of the discussion. Before that, people could still say Venus was probably active, maybe active, possibly active. After that, the argument became much sharper. If a vent changes shape and size that quickly, you're no longer just talking about old scars from a dead planet. You're looking at geology that was active on a timescale close enough to catch. And then in 2024, the case got stronger. Another analysis found additional surface changes consistent with fresh lava flows linked to eruptions during the Magellan era. That matters because one change can always raise caution. Scientists want to be careful. They want to rule out noise, geometry effects, interpretation mistakes. But when more than one line of evidence starts pointing in the same direction, the picture gets harder to dismiss. Venus stopped looking like a planet that was only active in deep history. It started looking like a planet active enough that we may already have seen it in action, without fully understanding what we were seeing at first. That is a very big shift. It means Venus is not just a world with an important past. It may be a world with ongoing geologic activity right now. And at that point, you might ask whether this came out of nowhere. Did scientists suddenly discover volcanism on a planet that had looked quiet before? Not at all. Magellan had already been warning us for years that Venus was a volcanic world. When Magellan mapped Venus, it showed a surface that was dominated by volcanic features. Roughly 85% of the surface appears to be covered in volcanic flows. There are lava plains spread across huge areas. There are long lava channels. There are volcanic domes and other unusual volcanic structures. Even before the newer studies, Venus already looked like a planet shaped heavily by volcanism. The surface was not subtle about it. It was already telling us that volcanic processes had played a major role in building and reshaping the planet. So the new discoveries did not invent the idea of volcanic Venus. They changed the timing. That is the key difference. The older picture said Venus is volcanic in the geological sense. The newer picture says Venus may be volcanically active in a much more immediate sense. That is a completely different level of importance, because now you're not only reconstructing ancient history, you may be watching an active world continue to rewrite itself. And once that becomes possible, the next question gets even deeper. If Venus is active, how is it actually losing its internal heat? That is where coronae become important. Coronae are these huge circular to oval features on Venus, and for a long time they were known to be unusual and important, but not fully understood. Recent NASA-backed work suggests that some of these coronae may be places where the outer shell of Venus is actively deforming and releasing heat from the interior. In plain language, Venus may have a way of staying geologically active without using Earth-style plate tectonics. That is a major point, because Earth's geology is usually explained with plate tectonics at the center of the story. Plates move, interact, recycle crust, and help the planet lose heat over time. Mars does not have Earth-like plate tectonics operating the same way, and Venus does not seem to either. So if Venus is still geologically alive without that system, then it may be using another route to stay active. And that means Venus is not just a hot planet with volcanoes. It becomes a challenge to one of the standard ways we think rocky planets work internally. That has big consequences. It means scientists may need to rethink how Earth-sized worlds evolve, how they dump heat, how their crust behaves, and how long they can stay active without looking like Earth. Venus may be showing that you do not need Earth's exact tectonic style to keep a planet dynamic. If that is true, then Venus is not just an odd case. It becomes a crucial comparison point for understanding rocky planets across the solar system and beyond it. And that is why this section changes the whole debate. Venus starts out looking like the old fossil planet, the one people forgot because it seemed too hostile and maybe too settled. But once you look at the newer evidence, that image starts to break. Venus may not be the dead world. Venus may be the unstable world. That is a very different kind of target. Mars is the world where you go looking for ancient lake beds, ancient rivers, ancient habitability, and maybe ancient life. A lot of the biggest Mars questions are about what the planet used to be. Venus may now be forcing a different kind of question. Not just what it used to be, but what it is still doing now. The crust, the mantle, the atmosphere, and the climate may still be interacting in a very active way. And if that is true, then going back to Venus is not only about filling in missing history. It is about catching a major rocky planet in the middle of an extreme process that is not finished. That changes the urgency. A geologically active Venus is not just another data point. It is one of the best chances we have to study how a large rocky planet can remain internally alive while also being climatically extreme. That is a rare combination. And it makes Venus look less like a solved world and more like a planet that could force major updates to planetary science. So now the pressure builds even more. Because if Venus is geologically active, then its surface and atmosphere are not separate stories. They may be linked right now. Volcanoes can feed gases into the atmosphere. The atmosphere can shape surface conditions. Over long timescales, geology and climate can push on each other until the whole planet changes state. And that leads straight into the next serious question. If Venus is still active, could it also preserve the biggest climate warning anywhere in the solar system? How far can a climate go before it stops being weather and starts deciding the fate of an entire planet? That is the real reason Venus matters so much. On Earth, climate change is usually discussed in terms of years, decades, or centuries. People talk about rising temperatures, changing rainfall, stronger heat waves, melting ice, and shifting coastlines. On Venus, the scale is much bigger. Climate did not just change conditions at the surface. Climate changed the whole identity of the planet. A thick carbon dioxide atmosphere, extreme greenhouse heating, and feedbacks that kept reinforcing the heating turned an Earth-sized world into a place with surface temperatures hot enough to melt lead. So Venus is not just a hot planet. Venus is what happens when atmosphere becomes strong enough to dominate almost everything else. And that is why Venus is so hard to reduce to one simple fact. It is not only hotter than it should seem at first glance, it is a planet where the atmosphere ended up overruling the basic advantages people usually focus on, like size and similarity to Earth. You can have a planet close to Earth in scale and still lose the balance completely. That is what makes Venus such a serious warning. It tells you that a rocky planet does not stay stable just because it starts in a promising category. Then the next question is obvious. If Venus is so dominated by its atmosphere, what is that atmosphere actually like? The first thing most people miss is that Venus does not have the kind of clouds they are used to thinking about. The visible cloud layers of Venus are not made of water droplets or ice crystals. They are made of sulfuric acid particles. That matters because it immediately tells you this is not just a hotter version of Earth's sky. The chemistry is different. The environment is different. Even the part of Venus that looks soft and bright from a distance is chemically hostile. But then Venus does something strange again. Those cloud layers sit at altitudes where pressures and temperatures can be much closer to Earth-like conditions than the surface below. That is one of the reasons Venus keeps forcing people to rethink their assumptions. The upper atmosphere can look relatively manageable in terms of pressure and temperature, while the surface below is one of the most extreme environments in the inner solar system. So Venus often feels like two planets stacked on top of each other. Higher up, some of the basic physics starts to look less impossible. Lower down, the planet turns into a crushing furnace. That split is one of the reasons Venus is so scientifically important. It is not just a uniformly simple hell world, it is layered. The atmosphere changes with altitude in ways that matter for chemistry, circulation, pressure, temperature, and mission design. That means when scientists study Venus, they are not only asking why the surface is so extreme, they are also asking how the atmosphere works as a system from top to bottom, and how that system evolved into what it is now. And once you start asking that, Venus stops being only a local solar system problem. It becomes part of a much bigger question. How do you tell whether a rocky planet far away is actually habitable, or only looks promising from a distance? That is where Venus becomes important far beyond our own planetary neighbourhood. Studying Venus helps scientists decode exoplanets, not just Earth, Mars, or the rest of the inner solar system. NASA researchers have used Venus transit data to study how a planet's atmosphere absorbs light. That matters because when astronomers observe distant exoplanets, they often have to read atmospheres indirectly by studying how starlight passes through them or interacts with them. Venus gives us a nearby test case for that kind of analysis. In simple terms, Venus helps train us not to fool ourselves. A rocky planet can look exciting from far away. It can be the right size. It can sit in a promising zone. It can sound like a possible Earth-like world. But Venus reminds you that appearances are not enough. A world can be rocky, Earth-sized, and still be completely hostile because of what happened in its atmosphere. So if you want to understand which exoplanets are realistic candidates for habitability, and which ones are false hopes, Venus becomes one of the most important comparison planets we have. That is a very big shift in how to think about it. Venus is not just a neighbour we should study because it is nearby. Venus is a reference case for reading alien worlds. It helps answer one of the biggest questions in modern astronomy. When we find a rocky planet, what are we actually looking at? That leads straight into another important point. If the atmosphere of Venus is so central to the whole story, then the atmosphere may still be holding key evidence we have not fully read yet. That is exactly why DAVINCI matters. DAVINCI is designed to probe Venus from above the clouds down toward the surface. It will measure atmospheric chemistry, noble gases, and the structure of the atmosphere in far more detail than older missions could manage. And those measurements are not just technical details for specialists. They matter because an atmosphere can act like a record of planetary history. It can preserve clues about water loss, volcanic outgassing, chemical reactions between surface and atmosphere, and the long-term evolution of the planet. That is why atmospheric science at Venus is not separate from the bigger story. It is the bigger story. If you want to know whether Venus once had more water, whether it went through a more temperate phase, whether volcanism has kept feeding gases into the air, or how the climate crossed into an extreme state, the atmosphere is one of the main places where those answers may still be stored. And that is what makes DAVINCI so important in this debate. It is not just going to Venus to collect new numbers. It is going to Venus because the atmosphere may still contain missing parts of the planet's history that could change how we understand the whole system. If those clues are there, they could help answer one of the hardest questions in planetary science. Was Venus always headed toward this outcome, or did it transform from something much milder into something catastrophic? And that question is where the stakes become much more serious. Because if Venus once had significant water, or even oceans, then Venus did not start as an obvious failure. It changed. That possibility is what makes Venus more than just a hostile neighbour. If Venus once had a more temperate past, then the lesson is much harsher than some planets are bad places. The lesson becomes that a planet with some Earth-like starting conditions can cross into a radically different state and stay there. A world can move past a threshold and not come back. That means habitability may be much less stable than people want to believe. And once you say that clearly, Venus becomes one of the most important cautionary planets in all of science. Not because it tells you that climate matters. We already know climate matters. Venus tells you that climate can become destiny at the scale of a whole world. It tells you that atmosphere can take over the story so completely that nearly every other familiar advantage stops mattering. That is why Venus is not only interesting, it is uncomfortable. It raises the possibility that Earth-like conditions are not something a rocky planet gets to keep automatically. They may be fragile, they may depend on long-term balances that can break, and if those balances break far enough, the result may not be a rough period that later settles down. The result may be a one-way shift. So now the argument gets even sharper. Mars tells you about a world that lost too much. Venus may tell you about a world that kept too much, heated too far and never recovered. One planet warns you about collapse through loss, the other may warn you about collapse through runaway excess, and that means the next question becomes unavoidable. If Venus may preserve one of the biggest climate warnings in the solar system, then why does Mars still own the conversation when people ask the biggest question of all? Was there ever life beyond Earth close to home? If Venus may hold the bigger climate warning, why does Mars still keep winning the life conversation? Because Mars gives you something Venus still does not. Clear, accessible evidence that the planet used to be wet in ways we can trace across the surface. That point is critical. The case for ancient water on Mars is not built on one strange signal or one speculative model. It is built from many layers of evidence that line up with each other. You see it in the geology, you see it in the minerals, you see it in the shapes of valleys, deltas, and ancient lake beds. You see it in the broader story of how Mars changed over time. Mars looks like a world that was once warmer, wetter, and more capable of supporting conditions that matter for habitability. That is why Mars keeps the advantage when the main question is past life. It is not only that Mars may once have had water, it is that the record of that water is still there in forms we can reach and study. NASA's MAVEN mission has spent years helping explain how Mars changed from a warmer and wetter planet into the cold, dry world we see now. That gives Mars a very powerful scientific setup. You are not just looking at a dead planet and guessing that something interesting might have happened long ago. You are looking at a planet with a visible climate loss story and a surface that still preserves parts of that story in accessible ways. And that matters because habitability is not an abstract idea. If you want to ask whether life might once have existed, you want places where water was present, where chemistry could happen, where sediments could preserve evidence, and where later missions can actually go back and check. Mars keeps winning because it gives you all of that in a way Venus still cannot match. Then the next question becomes more precise. Are we still just inferring what happened to the Martian atmosphere? Or are we actually measuring the process? We are measuring it. That is one of the biggest reasons Mars remains so strong scientifically. The story of its atmospheric loss is no longer just a broad theory. MAVEN has turned it into a measurable process. In 2025, NASA reported MAVEN's first direct observation of atmospheric sputtering at Mars. That is a process where energetic particles help knock atmospheric particles away into space. In simple terms, Mars is not just a planet that lost atmosphere somehow. Scientists are now catching one of the actual escape mechanisms in action. And earlier MAVEN work already showed something else that is just as important. Hydrogen escape rates from Mars can vary dramatically depending on the planet's distance from the Sun. That connects atmospheric escape directly to long-term water loss, because hydrogen is one of the pieces you track when you're trying to understand how water gets broken apart and gradually lost to space. So Mars is not just a world that used to be habitable and then stopped. It is a world where the physics of that decline is being measured in detail. That changes the whole tone of the Mars story. You're not only looking backward through rocks, you are also watching the long-term death mechanics of a planet through modern instruments. That makes Mars extremely powerful as a case study. It lets you connect ancient habitability, climate evolution, surface geology, and active atmospheric escape into one coherent picture. But then another practical point comes in, and this one matters a lot more than people sometimes admit. Even if Venus is the bigger mystery, Mars is still the better place to do field science. That is a huge advantage. On Mars, you can land rovers and drive them across the surface. You can drill into rocks. You can image sedimentary layers up close. You can analyze minerals. You can cache samples. You can revisit the same outcrop over and over. You can fly scouts like Ingenuity. You can spend months or years working through a landscape the way geologists actually want to work. Step by step, target by target, layer by layer. That changes what kind of science is possible. Mars research can behave much more like real-field geology. You can form a hypothesis, drive to a site, inspect it closely, compare it with nearby material, and keep refining your understanding as new observations come in. That is a very different level of access from what Venus currently allows on the surface. Venus surface science is still controlled by survival limits, so extreme that simply staying operational is a major challenge. On Mars, the environment is harsh, but it still gives machines room to keep working and gathering context over time. That is why Mars remains so strong even when Venus looks more disruptive in other ways. Mars is not just easier to imagine exploring, it is easier to do repeatable surface science there. That matters a lot when your goal is to look for signs of ancient habitability, or even possible biosignatures. Life-related geology is not something you want to study through a few short glimpses if you can avoid it. You want sustained access. Mars gives you that. And Mars is not only strong on the life question, it has also become much stronger as a geophysical planet. That is where InSight comes in. A lot of people think of Mars mainly as the place for rovers, rocks, and signs of ancient water. But InSight added another layer to the story. It detected more than 1,300 Marsquakes and helped scientists constrain the crust, mantle, and core of the planet. That means Mars is not only being studied at the surface, it is being studied internally. We now know much more about how Mars is built beneath the ground than we did before. That kind of knowledge matters for both science and future exploration. It tells you how the planet evolved internally. It helps refine models of planetary formation and cooling. It also supports future robotic and human planning because geophysical knowledge improves your understanding of stability, heat flow, structure, and broader environmental context. This is what repeated access buys you. Mars is not just being observed. Mars is being instrumented. More and more layers of the planet are being turned into something we can measure directly. And that repeated access changes the balance of the whole debate. Venus may still hold deeper surprises about climate, volcanism, and planetary evolution. But Mars already has a mature science environment that keeps expanding. It has atmospheric monitoring, surface mobility, seismology, mineralogy, high-resolution mapping, long-duration operations. It is the kind of accumulated investigation that lets one question feed directly into the next. So when you bring it back to the life question, the answer stays clear. If your single biggest question is ancient habitability and the possibility of past life, Mars still has the edge. It preserves surface records from a wetter past. Those records are accessible. They can be revisited. They can be drilled, imaged, sampled, and compared over time. Venus may still surprise us, especially if it once had a more temperate history than we currently think. But right now, Mars remains the stronger site for direct, repeatable, on-the-ground investigation of life-related geology. That is why Mars still owns this part of the conversation. Venus may be the bigger climate shock. Venus may be the more destabilizing planet for planetary theory. But Mars is still the better target for asking the question that most people care about first. Was there once life, or at least the kind of environment where life could have begun? And once you accept that, the next part gets much harsher. Because even Mars, the more practical option, is already dangerous at the edge of what humans may be able to manage, and Venus is worse. If Mars is the more realistic place for humans, that does not mean Mars is safe. It means the other option is even worse. That distinction matters because people sometimes talk about Mars as if it is the hard but manageable planet. It is hard, yes. Manageable is a much bigger claim. Mars is survivable only in the most technical sense. NASA's material on sending humans to Mars gives a temperature range from about minus 284 degrees Fahrenheit up to about 86 degrees Fahrenheit. That is a huge spread and most of it is hostile. Mars is a freezing desert with a very thin atmosphere, and that atmosphere does very little to protect you from radiation compared with Earth. So even before you start talking about food, fuel, habitats, medical support, dust, or psychology, the basic setting is already bad. This is not a backup Earth. It is not a place where humans can step out with the right jacket and some better tools. The atmosphere is too thin to breathe, the pressure is too low, the cold can be severe, and the radiation exposure is a constant problem. A human mission to Mars would already sit near the edge of what people can responsibly try. That is why every serious Mars plan becomes a systems problem very quickly. You need shielding, you need pressure control, you need thermal control, you need reliable power, you need life support that can keep working for a very long time with very little room for error. And even that description leaves out one of the most uncomfortable parts. The danger does not begin when you land. It begins on the way there. That point is easy to miss because people tend to picture Mars missions as a destination problem. Get to Mars, land safely, survive the surface, come home. But the cruise phase is part of the hazard. During Curiosity's trip to Mars, NASA's radiation assessment detector measured about 1.8 millisieverts of galactic cosmic radiation per day during cruise. That number matters because it reminds you that deep space is not a neutral hallway between Earth and Mars. The trip itself is part of the medical risk. So when you evaluate a human Mars mission, you are not adding surface danger on top of a normal journey. The journey is already part of the danger budget. The astronauts are exposed on the way out, exposed while they are there, and exposed again if they come back. That means shielding is not only a habitat issue, it is a transit issue. The ship matters, the mission duration matters, solar activity matters, the timing matters. A Mars mission is a radiation problem wrapped around a logistics problem wrapped around a survival problem. And that is still the more realistic human target. That is where the Venus contrast becomes brutal. Venus surface missions are not just hard, they are so hostile that they almost erase themselves. The pressure at the surface of Venus is around 90 to 92 times Earth's surface pressure. The temperature exceeds 460 degrees Celsius. Those numbers are not minor complications. They push almost every normal piece of space hardware toward failure. Electronics do not like that environment. Seals do not like it. Materials do not like it. Batteries do not like it. Thermal control systems do not like it. Communication systems are stressed by it. The environment attacks mission design at almost every level at once. That is why the Soviet surface survival record still feels extreme now. Venera 13 lasting 127 minutes is famous not only because it succeeded, but because that environment makes even a short success feel improbable. On Mars, mission teams talk about whether a rover might last for months or years. On Venus, the surface can reduce that discussion to minutes. Survival becomes the primary experiment. Before you ask what science package you want, you have to ask whether the machine can remain functional long enough to justify carrying one. And that difference changes the entire human comparison. Mars is dangerous because it gives you almost nothing for free. Venus is dangerous because it overwhelms everything you bring. So for people, the comparison is not really fair. Mars asks whether humans can build shelters, shield against radiation, make oxygen and other supplies, control pressure, manage dust, and survive long periods of isolation in a place that is naturally hostile. That is an enormous challenge, but it is still a challenge that can be broken down into engineering problems and operational plans. It is brutal, but it stays inside the category of problems you can at least try to solve step by step. Venus's surface is different. Venus' surface asks whether you can keep machinery alive long enough to matter. That is a lower bar than human settlement, and even that lower bar is already extreme. So when people jump straight to the idea of humans standing on the surface of Venus, they skip past the real issue. We are not close to making that a serious roadmap. The environment is too punishing. The heat is too high, the pressure is too high. The surface is not just an engineering challenge in the normal sense. It is an environment that starts destroying your operating margin immediately. That is why serious human exploration planning keeps circling back to Mars. Not because Mars is easy, not because Mars is kind, but because Mars at least offers a ladder. A very dangerous ladder, but a ladder. You can imagine precursor missions, resource experiments, habitats, mobility systems, radiation countermeasures, surface operations, and gradual expansion of capability. Venus's surface does not currently offer anything like that. It cuts that ladder off near the bottom. So if you are asking where humans go first, Mars still wins clearly. The risks are severe, but they belong to a category that space agencies can frame in terms of long-term development. Venus's surface is still in a category where the environment dominates the conversation so completely that human operations are barely the right question. But that is not actually the end of the Venus argument. Because Venus is not just its surface, that is the important twist, and it changes the whole shape of the debate. The worst part of Venus and the most interesting part of Venus are not the same place. They are vertically separated. The surface is one of the harshest environments in the inner solar system. But higher up in the atmosphere, the pressure and temperature become much more manageable than most people expect. Not easy, not friendly, but much closer to conditions that start sounding physically workable. And the moment you say that clearly, the question changes. It stops being, could humans ever stand on Venus? That version of the question pushes everything towards the surface, which is the most extreme zone and the least realistic one for people. The more interesting version is different. Could humans operate in the Venusian atmosphere instead? That sounds strange at first, but it is exactly the kind of strange idea Venus keeps forcing into the conversation. Mars is the planet where you think about bases on the ground. Venus may be the planet where the only serious long-term human concept is to stay above the ground entirely. And that is where the next section gets dangerous again. Because about 50 kilometers up, Venus stops looking completely impossible for a moment. And that single fact changes the whole debate. How can the most hostile planet near Earth also contain the closest thing to a human-friendly zone outside Earth? That is the twist that makes Venus so hard to ignore. Most people hear Venus and think the whole planet is one solid, impossible environment from top to bottom. That is not actually true. The surface is still one of the worst places in the inner solar system, but higher up the picture changes. At roughly 50 kilometers above the surface, about 30 miles up, the pressure is close to what you get at Earth's surface, and the temperatures are in a range of about 30 to 70 degrees Celsius. That is still hot. It is not pleasant. It is not casual. But compared with the surface below, it is a completely different world. And that matters because the old assumption falls apart right there. Venus is not uniformly unusable. It has layers, and one of those layers is far less extreme than the inferno under it. That does not suddenly make Venus easy. It does something more interesting than that. It makes Venus complicated in a way most people do not expect. The same planet that crushes and bakes machines at the surface also contains an altitude band where the pressure-temperature combination is much closer to something engineers can at least talk about seriously. That is why this part of the Venus story changes the whole debate. If you only think about the surface, the case seems closed. Humans do not go there. Long-term missions do not go there. Settlement is not even a serious near-term discussion. But once you move the conversation upward into the atmosphere, the answer stops being simple. Venus stops looking like a totally closed door and starts looking like a strange engineering problem with a narrow zone of possibility built into it. And that is exactly why balloon and aerostat ideas keep coming back. Because once you have an atmosphere thick enough to provide buoyancy, and once you have an altitude band where pressure and temperature are much more manageable, floating platforms stop sounding like pure fantasy. They start sounding like a weird but defensible engineering direction. You do not need to land and survive on the ground if the atmosphere itself can support systems above the ground. That is the key idea. Venus may be one of the only places where the atmosphere is not just a problem. It may also be part of the platform. That is a very different kind of logic from Mars. On Mars, the whole discussion pushes you toward the surface. Land there, drive there, dig there, build there, protect yourself there. Venus changes that logic. Venus suggests that if you want long-duration presence, you may not go down and build up. You may stay suspended and operate inside the atmosphere itself. And that is why these concepts do not go away. They are not attractive because they are simple. They are attractive because the physics gives them a narrow opening. In that altitude band, a floating research platform or long-duration atmospheric station becomes conceptually possible in a way a surface base does not. It is still difficult, it is still risky, but it moves Venus out of the category of obviously impossible and into the category of possible in a very strange way. And space exploration has a long history of moving toward exactly those kinds of problems. If a place offers a serious scientific payoff, and there is even a narrow physical path to operating there, engineers will keep looking at it. But then the problem hits immediately. That altitude band may be milder in pressure and temperature, but it is not friendly. The catch is acid. Venus's cloud particles are made of sulfuric acid, not water. That means an atmospheric platform would not be floating in something remotely like Earth air. It would be operating in a corrosive environment where chemistry becomes part of the survival problem every second. Materials matter more. Coatings matter more. Seals matter more. Windows and optics matter more. Power systems matter more. Long-duration maintenance becomes much harder. Every exposed surface has to be designed with chemical attack in mind. So the atmospheric sweet spot is real, but it is not some hidden paradise. It is just a zone where one set of extreme problems drops enough that another set of hard problems becomes worth discussing. You escape the crushing surface pressure and furnace level heat, but you do not escape danger. You move into a different danger. A corrosive one, a systems engineering one, a long-duration reliability problem where the environment may not destroy you in minutes, but it will still keep attacking your hardware. That is why Venus atmospheric ideas feel both exciting and frustrating at the same time. The physics opens a door, but the chemistry stands right in the doorway. And once you accept that, the whole image of Venus starts to change. Venus stops being the planet of surface colonization concepts and becomes the planet of aerial civilization concepts. That is a very different kind of future. Mars naturally leads people toward images of habitats on the ground, tunnels under the soil, regolith shielding, surface vehicles, drill systems, and industrial outposts. Everything about Mars pushes the imagination downward into the terrain. Venus pushes the imagination upward. Floating labs, drifting stations, atmospheric chemistry platforms, high-altitude robotic networks. Maybe much later, crude aerostats if the materials, systems, and economics ever become good enough. That difference is not just visual, it changes the whole architecture of survival. Mars says build against scarcity. Venus says stay above the worst zone entirely. Mars says hold pressure in. Venus says find the altitude where pressure is already workable, and then defend against chemistry instead. Mars says use the surface as your base. Venus says the surface may never be your base at all. That is why Venus is so conceptually disruptive. It forces a completely different model of what presence on another world could look like. Not a colony planted on the ground, not a settlement built into rock, something more like a persistent atmospheric outpost held aloft inside a planet that is still trying to destroy it in slower ways. And that kind of idea changes the emotional balance of the Mars versus Venus debate. Mars is the more familiar future. Venus is the stranger one. Mars fits how people already think about expansion. Venus forces a different idea of expansion altogether. But that does not mean Venus wins the argument, not even close, because the jump from conditions there are less extreme than the surface to humans can live and work there safely and economically is enormous. Right now, we do not have long-duration Venus aerostat infrastructure. We do not have operational acid-resistant habitats working at scale. We do not have closed-loop systems proven for that environment over years. We do not have a mature roadmap, anything like the one Mars has built through repeated missions. We do not have the supply chain, the mission cadence, or the flight heritage that would let anyone speak casually about a human Venus atmosphere program. That is the part that has to stay honest. The atmospheric sweet spot gives Venus plausibility, not victory. It makes the planet much more interesting. It keeps some human-related concepts alive. It turns a total no into a difficult maybe in one narrow layer of the atmosphere. But it does not erase the scale of what is still missing. Venus has not solved the engineering case. It has only made that case worth thinking about. And in some ways that makes Venus even more dangerous as an idea. Because now it is not just the impossible planet, it is the planet that offers one narrow path and then dares you to build an entire exploration strategy around it. So the real takeaway here is not that Venus is secretly easier than Mars. It is that Venus contains a small zone where the rules suddenly become less hopeless. And that is enough to keep the planet in the conversation. Mars still leads for human missions because the path is clearer, the experience is deeper, and the operational logic is much more mature. But Venus refuses to stay out of the argument because at 50 kilometers up, it stops looking completely closed off. And that makes the next question unavoidable. Even if Venus has a strange atmospheric opening, Mars still has something Venus does not: the beginnings of a real industrial story. How do you know a planet is moving from exploration into something more serious? You know because you stop only studying it and start using it. That is one of Mars' biggest advantages over Venus right now. Mars is where in situ resource use stopped being a concept slide and became real hardware doing real work on another planet. NASA's MOXIE experiment, riding on Perseverance, took carbon dioxide from the Martian atmosphere and turned it into oxygen. Across 16 runs, it produced 122 grams total, reached rates up to 12 grams per hour, and delivered oxygen at least 98% purity. On human scales, that is tiny. Nobody is building a settlement out of 122 grams of oxygen, but that is not the point. The point is that the chemistry worked on Mars, not just in a lab on Earth. That is a major shift in how you think about the planet. Before something like MOXIE, Mars was mostly a place you visit and survive for a while, with everything important brought from home. After something like MOXIE, Mars starts to look like a place where local materials can be turned into useful products. That changes the whole strategic picture, because the moment you can do that even at a small scale, you're no longer only asking how to land there, you're asking how to operate there. And that is exactly why the number can be small while the milestone is huge. MOXIE was never supposed to solve settlement. It was supposed to prove a path. It was supposed to show that Martian atmospheric carbon dioxide can be processed on Mars into something you actually need. Oxygen matters for breathing, of course, but it also matters for propellant systems. That is why this experiment lands so hard strategically. Once you prove that the local atmosphere can be turned into a life support input or part of a fuel chain, Mars stops looking like a completely closed environment. It starts looking like a place where engineering can create footholds. That word matters here. Footholds. You do not go from one oxygen experiment to a city. That is fantasy. What you do get is a first foothold in the logic of becoming operational off Earth. You prove the chemistry, then you ask how to scale it, then you ask how to power it, harden it, automate it, repair it and integrate it with habitats, storage systems, transport systems and return missions. The first step is small because first steps usually are. But once that first step works in the real environment, the entire conversation changes. That is why Mars looks different now than it did 20 years ago. It is not just a science target anymore. It is becoming a place where people can seriously talk about production, even if only at the earliest stage. And MOXIE is not standing alone. That is another reason Mars keeps pulling ahead in the practical argument. Mars has a widening mission ecosystem, not isolated stunts. That difference matters a lot. NASA has 5 active missions at Mars. ESA's Rosalind Franklin rover is targeting launch in 2028. That is what a maturing exploration theatre looks like. You have multiple agencies, you have orbiters and surface systems, you have missions that are not just trying to survive, but trying to add another layer to an already existing framework. New projects do not arrive at Mars as if nothing came before them. They arrive inside a growing structure of maps, lessons, landing knowledge, weather understanding, relay systems, geological context, and operational memory. That kind of ecosystem is extremely valuable. It means Mars is ahead not just scientifically, but institutionally. Agencies know how to justify missions there. Engineers know how to design for it. Scientists know how to build on past work. Program managers know there is a roadmap, not just a gamble. That lowers friction. It lowers uncertainty. It makes it easier to turn one success into the next mission, instead of restarting the whole argument every time. And that is exactly where Venus still struggles. Venus absolutely has resources. It has a huge carbon dioxide atmosphere. It has sulfur-bearing chemistry. It has a dense atmospheric system full of scientifically rich material. In theory, there is no shortage of matter there to work with. The issue is not abundance. The issue is pathway. We do not yet have the Venus equivalent of MOXIE. We do not have a proven piece of hardware that went into real Venus conditions and demonstrated useful industrial processing in situ in a way that opens the door to scaling. That is the difference. Venus has ingredients. Mars has a first industrial proof point. That does not mean Venus is empty of potential. Far from it. Futurists can point to the atmosphere, the chemistry, and the strange advantages of the high-altitude zone and say there is something there to work with. And that is true. But right now, that remains mostly conceptual. Mars owns the first actual hardware milestone in turning off-world atmosphere into a directly useful product under real planetary conditions. And that matters because real programs are built on tested footholds, not only on interesting ideas. This is why Mars still looks like the first place humans might try to become operational in a serious sense. Not comfortable, not easy, not safe, operational. That is a different standard. Mars is harsher than most people imagine, but it keeps rewarding engineering with something incredibly important. Traction. You can move there with rovers. You can fly scouts there. You can do field geology there. You can run oxygen generation experiments there. You have decades of environmental data there. You have a growing stack of mission heritage there. Every one of those things is a piece of a ladder. No single step solves the Mars problem, but the ladder is real. Venus still offers the bigger mystery in a lot of scientific ways. Venus may be the more explosive target for climate history, planetary evolution, volcanism, and rocky world theory. But when the question becomes operational instead of purely scientific, Mars pulls ahead hard. Mars gives you a clearer ladder from exploration to use. Venus gives you interesting possibilities, but not the same tested sequence. And that difference becomes enormous the moment budgets, schedules, and choices get involved. Because once people have to decide where to put serious money, they do not only ask which planet is most fascinating, they ask which planet lets each mission build toward the next one. Mars has a much better answer to that question right now, so the practical balance stays sharp. Venus may be the more disruptive planet for theory. Mars is still the stronger planet for operations. Venus may change how we think. Mars is already changing how we build. And that leads straight into the next hard divide between the two worlds. Because the deeper you compare them, the clearer it gets that they do not just demand different hardware. They demand completely different engineering philosophies. How can two planets both be hard but in completely different ways? That is the next thing you have to understand, because Mars and Venus do not just ask for different missions, they ask for different engineering instincts. If you treat them like the same kind of challenge, you misunderstand both of them. Mars engineering is mostly about scarcity. Venus engineering is mostly about excess. And that one contrast explains a huge amount of the difference between the two worlds. Start with Mars. Mars is a planet of not enough. Not enough atmosphere, not enough pressure, not enough warmth, not enough protection from radiation, not enough readily usable liquid water sitting out on the surface. Almost every system you design for the Mars is trying to compensate for something the environment is not giving you. If you want the people there, you need habitats that hold pressure because the outside air is far too thin. You need shielding because the atmosphere does not protect you the way Earth's does. You need to conserve heat because the environment is cold. You need life support because there is no breathable air. You need to extract useful materials from a thin atmosphere and from buried or hard-to-reach resources because almost nothing is available in a convenient form. That is the basic Mars pattern. The planet is not constantly crushing your systems with overwhelming conditions. It is forcing you to bring or make what it refuses to provide. That is why Mars engineering becomes a discipline of compensation. You're always filling a gap, always building against absence, always making up for what is missing, and that shapes everything. A Mars habitat is not just a building. It is a pressure vessel, a radiation defense system, a heat management system, a dust control system, and a life support system all at once. A Mars vehicle is not just transport, it is survival infrastructure. Even a simple surface operation becomes a chain of support problems because the environment gives you so little margin. Mars punishes you by making you work for every basic condition that Earth normally gives you for free. Then you flip to Venus, and almost everything changes. Venus is not a planet of lack. Venus is a planet of too much atmosphere, too much heat, too much pressure near the surface, too much corrosive chemistry in the cloud layer, too much thermal stress, too much environmental force pressing on every design limit you have. Systems at Venus do not usually fail because the world is missing something you need. They fail because the world delivers so much of the wrong thing that your tolerances disappear. That is a very different engineering problem. On Venus, the environment itself can become stronger than the design logic you would normally trust. Materials that are fine elsewhere become weak links. Electronics that work on other planets overheat or break down. Seals, batteries, thermal systems, coatings, and communication hardware all enter a much harsher operating regime. At the surface, the problem is not whether you can build a useful machine in theory. The problem is whether the environment starts degrading that machine immediately in multiple ways at once. So Mars and Venus do not just differ in degree, they differ in style. Mars says you are on your own, because the planet is not giving you enough. Venus says you are under assault because the planet is giving you too much. One world makes you compensate for missing support, the other world makes you survive overwhelming conditions, and once you see that, another difference becomes much clearer. Mars mobility has become real in a way Venus mobility still has not. That is a huge practical advantage for Mars. Rovers have been driving there for years. We have already built a real tradition of surface traversal on Mars. Not just one lucky drive, but a long sequence of missions proving that mobility can be sustained, improved, and turned into a science strategy. Then ingenuity added something even bigger. Powered flight on another planet. 72 flights. That means Mars is not only reachable and landable, it is traversable in more than one mode. That matters because it opens up layered engineering. You can think in terms of orbiters above, landers on arrival, rovers on the ground, helicopters scouting ahead, and maybe one day human vehicles moving between sites. That is what iterative systems design looks like. One layer supports the next. One mobility mode expands the reach of another. The environment is still harsh, but it allows this kind of step-by-step growth. Engineers can test, learn, adapt, and extend capability over time. That is a major reason Mars feels increasingly operational. It is not just that we can get there. It is that once we arrive, the planet lets us do more than one kind of movement and more than one kind of mission profile. That is exactly how an exploration program matures. Venus is more complicated. Venus can actually help you during arrival. Its atmosphere is so thick that it can be useful for aerobraking and related entry concepts. That is a real asset. It means Venus is not difficult in every phase the same way. In some parts of mission design, the atmosphere gives you something Mars does not. It can help slow you down. It can help shape orbital strategies. It can support mission concepts where atmospheric interaction is part of the plan rather than only a danger. But that advantage comes with a severe cost. The same atmosphere that can help you arrive becomes a major problem if you need to keep operating for a long time, especially lower in the atmosphere or near the surface. This is where the distinction becomes very sharp. Mars is hard to land on. Venus is hard to remain on. Those are not the same problem, and they produce very different exploration cultures. A Mars mission worries intensely about entry, descent, and landing, because the atmosphere is thin enough to make landing difficult but thick enough to complicate it. Then if you succeed, you may get years of surface science. A Venus mission may have some advantages during approach because of atmospheric braking, but once you push deeper, the environment can start cutting down your survival time fast. So the main question shifts. It is not only can you get there, it becomes how long can anything keep working after arrival? That difference changes the whole mindset of mission design. Mars encourages follow-up. Venus forces endurance thinking from the start. Mars lets you ask how to expand operations after landing. Venus makes you ask how to keep operations alive at all. And that is why these planets do not just demand different hardware, they demand different mental models. Mars is mainly a logistics and settlement problem. A brutal one, but still that kind of problem. How do you deliver mass? How do you protect people? How do you build habitats? How do you move across the surface? How do you make supplies locally? How do you turn repeated missions into a functioning operational chain? Mars keeps pushing you toward build-up, toward infrastructure, toward accumulation of capability. Venus is mainly an endurance and environment problem. How do you design for heat, for pressure, for corrosive chemistry, for limited survival windows, for atmospheric operation without safe access to the surface? How do you keep anything alive long enough to justify sending it there in the first place? Venus pushes you towards survival under continuous stress. Not expansion first, durability first. That is why a Venus-first strategy would not just mean choosing a different target, it would mean choosing a different engineering doctrine at a very deep level. Mars says build systems that can grow. Venus says build systems that can endure. Mars asks how humans might eventually live there. Venus asks how hardware or habitats could stay functional long enough to matter. Mars is about scaling presence. Venus is about surviving the environment. And that is exactly why the next part of this debate gets uncomfortable. Because once you stop thinking only about engineering difficulty and start thinking about scientific return per dollar, Venus starts looking dangerous again. Mars may be the safer investment, but safer does not always mean better value scientifically. Why does Mars keep getting the bigger budgets even when Venus may be hiding the bigger unanswered science? Because Mars is the safer investment. Not safer in a physical sense, safer in a program sense. Agencies know how to spend money at Mars. They know what a Mars mission looks like. They know the communication setup, the landing problems, the science planning, the relay support, the risk categories, and the kinds of teams and timelines that work there. Mars missions fit an existing pipeline. There is already mission heritage. There is already institutional confidence. There is already a shared understanding of what you are buying when you fund another Mars project. That matters more than people think. In big science programs, uncertainty is expensive, and if a destination already has proven mission architecture, known operational patterns, and decades of accumulated lessons, then every new project starts from a stronger position. You do not have to argue from zero. You do not have to rebuild the entire case every time. Mars benefits from that. It has become a place where spending can be defended not just scientifically, but bureaucratically. The system knows how to work with Mars, and that creates a major advantage. When a planet already has a functioning exploration pipeline, every new mission looks less like a gamble and more like a continuation. That makes proposals easier to justify. It makes scheduling easier to defend. It makes mission design more predictable. Mars is not just ahead in data, it is ahead in institutional familiarity. But that raises a harder question. If Mars is the safer place to spend money, does that automatically mean it is the best scientific bargain? Not necessarily. In fact, Venus may be the riskier investment and the better bargain scientifically. The reason is simple. Venus has been underexplored for so long in modern times that the scientific return from even a few strong missions could be enormous. When ignorance is deep, new data lands harder. At Mars, a lot of the big framing is already established. We still have major questions, but we also have a huge base of knowledge. At Venus, some of the most basic high-value questions are still open. Is the planet volcanically active right now? How exactly does it lose interior heat? What is its tectonic style if it does not work like Earth? What is the composition of the tessera terrain? How much water did it once have? Did it ever pass through a more habitable phase before becoming what it is now? Those are not small details. Those are first-order planetary questions. They connect directly to climate evolution, surface evolution, atmospheric chemistry, rocky planet habitability, and even exoplanet interpretation. And because modern Venus data is still so incomplete compared with Mars, a relatively small number of successful missions could force big updates fast. That is why Venus may be a better scientific bargain, even if it is a harder engineering and programmatic bet. This is the basic economic tension. Mars gives you lower uncertainty and a stable return. Venus may give you higher uncertainty and a much bigger marginal return per new mission. And the most interesting part is that agencies already seem to understand this. You can see it in the 2030s mission stack. DAVINCI is aimed at atmospheric descent science. It is meant to probe the atmosphere directly, measure chemistry and noble gases, and help answer major questions about water history, atmospheric evolution, and surface-atmosphere interaction. VERITAS is aimed at global geology and topography. It is built to give Venus much better radar maps and much better geologic context than we have now. EnVision is designed to study Venus from the core to the upper atmosphere using radar and other instruments, with planned ground resolution on the order of 10 meters. That lineup matters because it is not random and it is not redundant. These missions are attacking different parts of the same big problem. One focuses on the atmosphere and descent measurements. One focuses on surface geology and topography. One is built to connect the deep interior, surface processes, and atmospheric system together. That is a serious science strategy. It shows that major agencies are not looking at Venus as a side curiosity. They are treating it like a planet with major unanswered science that is finally worth attacking in a coordinated way. And that should tell you something important. When agencies with limited budgets and long planning cycles start building multiple major Venus missions into the same decade, they are signaling that the scientific leverage is real. They are saying in effect that Venus has been left under-examined for too long, and that the payoff from returning could be unusually high. Then there is the public side of this, and this is where the picture gets distorted. Mars still dominates the narrative because Mars is easier to sell. People can picture Mars. They can imagine standing on it, driving across it, building habitats on it, planting flags on it. It fits the human expansion story almost perfectly. Venus does not. Venus sounds hostile, corrosive, and impossible. It sounds like a place where everything goes wrong. That makes Mars easier to market and Venus harder to dramatize in the usual way. But public narrative is not the same thing as science yield. A destination can be easier to imagine and still not be the place with the biggest unanswered questions. Science does not have to follow the planet that feels most cinematic. In fact, some of the best science often comes from the place that breaks your expectations most directly, because that is where your models are weakest. That is where you are least likely to be coasting on familiar assumptions. And right now, that description fits Venus very well. Mars inspires because it looks like a frontier. Venus threatens simple ideas about climate, geology, and Earth-like planets. That makes Mars more comfortable for long-term public storytelling. It may also make Venus more valuable for pure scientific disruption. And that is where the strategic question becomes uncomfortable. If 1 decade of serious Venus missions could change how we understand climate evolution, active volcanism, planetary resurfacing, tectonic behavior without Earth-style plates, water loss, rocky exoplanets, and the long-term stability of habitable worlds, then underfunding Venus may be one of the biggest opportunity costs in planetary science. That is the uncomfortable version of this debate. Maybe Mars is not overfunded because it is unimportant. Mars absolutely matters. The harder possibility is that Venus has been underfunded relative to how scientifically explosive it could be. That is why this is not just a debate about preference. It is a debate about return on ignorance. At Mars, we are adding depth to a mature picture. At Venus, we may still be missing pieces so basic that a few well-placed missions could rearrange the whole field. That kind of leverage is rare, so the strategic split becomes very clear. Mars is the comfortable frontier. Mars is where agencies know how to build, justify, and sequence missions. Venus is the more dangerous scientific target because the unknowns are larger and the answers may hit harder. One is easier to fund, the other may be more costly to ignore. And once you follow that logic all the way out, the next step is obvious. Venus is not just important for understanding our own solar system. It may change how you interpret every Earth-size exoplanet you hear about. Why does Venus matter so much for planets we will never visit? Because every time astronomers find a rocky planet around another star, the first public question is almost always the same. Could it be like Earth? And that sounds reasonable until you remember something important. In our own solar system, the closest comparison to Earth in size is not only Earth itself, it is Venus. And Venus is the warning built into the dataset. So when people hear rocky and Earth size, they often hear possibly habitable. But Venus is the proof that those labels are nowhere near enough. That changes the whole mood of exoplanet science. A rocky planet can be the right size and still be a complete disaster. A planet can sit in a promising category and still end up with a crushing atmosphere, extreme greenhouse heating, and surface conditions that erase almost everything people mean when they say Earth-like. So every rocky exoplanet you hear about is shadowed by Venus, whether people say it out loud or not. Venus is the counterexample living right next door. It tells you that size is not safety, rock is not safety, even being broadly similar to Earth is not safety. And that matters because exoplanet discovery is moving faster than exoplanet understanding. We can find worlds much more easily than we can truly interpret them. We can estimate size, we can estimate orbit, sometimes we can estimate mass, sometimes we can get hints about atmosphere, but that is exactly where Venus becomes dangerous in the best scientific sense. Venus tells you that a world can look promising from far away and still be the wrong answer. So the next question gets sharper. How do you stop fooling yourself when you look at alien worlds from a distance? One answer is Venus. NASA researchers have used Venus transit observations to study how a planet's atmosphere absorbs light, because those lessons matter for exoplanets. That sounds technical, but the basic point is simple. When a planet passes in front of a star, some of the starlight filters through the atmosphere. By studying how that light changes, scientists can learn something about what the atmosphere is made of and how it behaves. That is one of the main tools for reading distant worlds. And Venus is extremely useful here because it helps train us against false hope. A planet can have an atmosphere that looks interesting or promising in simplified descriptions, but the real climate underneath can still be extreme. Venus teaches caution. It teaches that a thick atmosphere is not automatically a good sign. It teaches that a world can look bright, substantial, and planet-like while being completely hostile at the surface. In other words, Venus helps scientists avoid reading optimism into incomplete data. That is why Venus matters so much beyond our own system. It is not just a nearby planet with a strange climate. It is a calibration case for reading rocky worlds properly. If you want to understand how atmospheres can mislead you, Venus is one of the best places to learn that lesson. A distant planet may look exciting because it has some Earth-like traits. Venus reminds you to ask the harder questions. What is the atmosphere actually doing? How much heat is it trapping? Did the world lose its water? Did greenhouse feedbacks take over? Did the planet cross into a state that looks stable from far away but is catastrophically uninhabitable in reality? Then you bring Mars back into the frame and the full picture gets much stronger. Mars and Venus together bracket the habitability problem. Mars shows one kind of planetary failure. A world can lose atmosphere, lose water, cool down, dry out, and become a cold desert. Venus shows the opposite kind. A world can keep a massive atmosphere, trap too much heat, and push itself into extreme overheating. Earth sits between those two outcomes. That is why studying both planets is so important. They are not just interesting neighbours. Together they define the boundaries of what can happen to rocky worlds. And that leads to a much more serious conclusion. Habitability may not be some broad and easy default for Earth-sized planets. It may be a narrow corridor between two common disasters, too little atmosphere and water, and you get something like Mars, too much greenhouse trapping and climate feedback, and you get something like Venus. Earth looks less like the standard model, and more like the narrow middle case that stayed balanced. That is a very big deal for exoplanets, because if Earth is the narrow middle and Mars and Venus are the failure modes on either side, then finding an Earth-sized world in a promising orbit is only the start of the story. The real question is whether that world stayed in the corridor or left it. Did it fade out? Did it overheat? Did it lose water? Did it hold too much gas? Did geology and atmosphere keep each other in balance? Or did they drive the planet into one of the bad outcomes? And once you frame the question that way, Venus starts to move toward the centre of planetary climate theory. Mars is still stronger for robotic field science. Mars is still the better target for surface operations, repeated geology, and maybe one day human crews. But if your real question is not where do people go first, and instead what controls the fate of rocky planets, then Venus may actually be more important. Because Venus forces you to deal with climate feedbacks, atmospheric chemistry, outgassing, water loss, long-term greenhouse behaviour, and the ways those processes can rewrite an Earth-sized world over billions of years. That is why Venus feels scientifically larger than its position. Publicly, Mars stays on top because people can imagine boots, habitats, rovers, supply chains, and eventual human presence. Mars fits the expansion story. Venus does not. Venus sounds like a place where nothing should work, and that makes it harder to rally people around in the same way. But science does not care which planet is easier to sell. Science cares which planet breaks your models hardest. And right now, Venus may be the more destabilizing planet in that sense. It threatens simple ideas about Earth analogues. It threatens easy exoplanet optimism. It threatens the assumption that Earth size means roughly Earth-like. Mars gives you a frontier story. Venus gives you a correction. Mars invites expansion. Venus forces humility. That mismatch is exactly why Venus can feel scientifically bigger than it looks. Publicly, Mars is still the flagship because it is easier to turn into a roadmap people can picture. Scientifically, Venus may hit harder because it forces deeper questions. Not just where humans go, but how worlds stay habitable, how climates fail, and how often Earth-like might actually be the wrong first guess. And that is why this debate keeps getting sharper instead of simpler. Mars may still be the planet we reach first, but Venus may be the planet that changes what we think we are looking for everywhere else. And now the tension moves into the future, because this argument does not have to stay theoretical for much longer. The 2030s could be the decade that finally forces Mars and Venus into a direct strategic comparison. When does this argument stop being theoretical and start turning into real evidence? The answer may be the 2030s. That is why this next decade matters so much. For a long time, Venus arguments were easy to push aside because the mission stack was thin. You could say Venus was interesting, maybe even important, but still not a real near-term priority. That excuse is getting weaker. The 2030s are shaping up to be the decade when Venus goes from underexplored and mostly discussed in theory to directly tested by multiple serious missions. If those missions do what they are supposed to do, the whole balance of the Mars versus Venus debate could change fast. Start with DAVINCI. NASA currently lists it with a tentative 2030 launch, and its target is not vague. It is aimed straight at the atmosphere and the lost history problem. DAVINCI is designed to investigate Venus from above the clouds down toward the surface, measuring atmospheric chemistry, noble gases, and the structure of the atmosphere in detail as it descends. It is also expected to capture images during descent, with special interest in areas like Alpha Regio, a region that may preserve clues about older terrain and possibly deeper history. That matters because DAVINCI is not just another pass-through mission. It is built to attack one of the hardest questions directly. What did Venus used to be? If the atmosphere still holds clues about water loss, volcanic outgassing, and long-term climate evolution, DAVINCI is the kind of mission that can start pulling those clues into a coherent story. If Venus once had more temperate conditions, if it once held much more water, if its atmosphere still remembers major transitions in its past, this is one of the missions most likely to help reveal that. So DAVINCI is not a vague gesture toward Venus. It is a focused attempt to force answers out of the atmosphere itself. Then you get to VERITAS, and this is where the geology side of the story becomes much more serious. VERITAS is currently listed no earlier than 2031, and its job is to become the geologic truth machine for Venus. It will build much higher quality radar maps and topography than we had from Magellan, and that's a big deal. This is not just about making better looking maps. The point is to identify active geologic processes, understand the history of resurfacing, map tectonic and volcanic structures much more clearly, and connect surface features to the internal evolution of the planet. That is why VERITAS matters so much. If Venus is still geologically active, if it is still reshaping itself, if volcanism is ongoing, if coronates and other structures are telling us something new about how an Earth-sized world loses heat without Earth-like plate tectonics, then VERITAS is built to catch that. It will not solve everything by itself, but it can dramatically improve the geologic foundation of the whole Venus story. And once that foundation gets stronger, a lot of arguments that are still semi-open today will become much harder to dodge. Then the picture gets even bigger, because this is not just an American return to Venus. ESA's EnVision brings Europe into the Venus return in a serious way. EnVision is planned for launch in November 2031. The mission profile includes about 15 months of cruise, around 11 months of aero braking before it reaches its final science orbit, and then a 4-year science phase. ESA says the mission will study Venus from its core to its upper atmosphere using 6 instruments, including radar imaging expected to reach ground resolution on the order of 10 meters. That is a very strong signal. It means Venus is not being treated as a one-off curiosity by one agency. Multiple major agencies are planning complementary missions in the same decade, and EnVision's scope makes the point even clearer. This is not a narrow mission looking at one small corner of the problem. It is built to connect the deep interior, the surface, and the atmosphere into one planetary system story. Once a mission is designed at that level, you are no longer dealing with background interest. you're looking at a real return to Venus as a first-order scientific priority. So when you put DAVINCI, VERITAS and EnVision together, the message is obvious. Venus is no longer an afterthought in major agency planning. The next decade could be the first time in a very long time when Venus gets a mission lineup strong enough to start answering its biggest unresolved questions in a coordinated way. But this is where the section has to stay balanced. Mars is not freezing in place while Venus wakes up. Mars still has 5 active NASA missions. It still has the strongest continuity of any planetary exploration program beyond Earth. ESA's Rosalind Franklin rover is targeting a 2028 launch. Mars still has the advantage in operational depth, long-term infrastructure, repeat surface access, and follow-on science. So the 2030s are not about Mars being replaced. They are not about Mars suddenly becoming less important. They are about Venus finally re-entering the competition at a serious level. That distinction matters because people sometimes react to a strong Venus case as if it must mean Mars is being downgraded. That is not really the point. Mars remains the more mature exploration theatre. It remains the better target for long-duration surface science, operational build-up, and eventually human missions. What changes in the 2030s is that Venus may finally stop being the underexplored outlier and start becoming a full strategic counterpart. And that is why the next decade is not just about more missions. It is a test of priorities. If DAVINCI, VERITAS, and EnVision deliver strong results, Venus could move from being the hostile planet everyone already thinks they understand to becoming one of the central reference worlds for climate evolution. Active geology, water history, and the long-term fate of rocky planets. It could become one of the most important planets for understanding why Earth-like worlds stay stable or fail. It could become a key reference point for exoplanet interpretation. It could become the place where several big planetary science arguments get rewritten at once. At the same time, if Mars keeps building operational capability, climate loss science, sample strategy, mobility systems, and long-duration field geology, then the old hierarchy may not survive in its current form. Instead of one planet dominating the whole inner solar system conversation, you may get a cleaner split. Mars becomes the main target for humans, surface operations, and sustained field science. Venus becomes the main target for the deepest unanswered questions about climate catastrophe, geologic activity, and rocky world habitability. That would be a major shift. Not Mars losing, not Venus suddenly winning everything. A division of roles based on what each planet is uniquely best at teaching us. And if that happens, then the original title question starts to resolve in a very sharp way. The answer may not be Venus instead of Mars. It may be that the old habit of treating Mars as the obvious first answer to almost every big planetary question stops making sense. Because if Mars keeps owning the path to human operations, and Venus starts owning the path to the deepest planetary unknowns, then the future gets split in two. One world tests how far our machines and bodies can go. The other tests whether we really understand why worlds like Earth survive at all. And that means there is only one section left. Once you have followed all of this through science, engineering, habitability, operations, and the 2030s mission stack, the verdict has to be clear. So where does this actually land? If the question is where humans should go first, the answer is still Mars. That part should be clear by now. Mars is not easy. Mars is not safe. Mars is not close to Earth in any practical human sense. But Mars is still the more plausible first human destination because its dangers can be turned into engineering problems that we already know how to define. You need shielding. You need habitats. You need pressure systems, you need radiation protection, you need mobility on the surface, you need ways to extract useful materials from the environment, you need to manage power, dust, isolation, and mission length. Those are all severe problems, but they are problems with a visible ladder. That is the key difference. Mars gives you a ladder. NASA is explicitly working on technologies aimed at future human Mars missions. Mars already has the kind of robotic groundwork a human program would need. We have orbiters, rovers, landing experience, environmental data, surface operations, sample strategy, and even an experiment like MOXIE, showing that the atmosphere can be turned into oxygen. That does not mean humans are close to settling Mars. It means Mars already has the early pieces of a roadmap. There is sequence. There is build-up. There is a path from robotic exploration towards something more operational. Venus does not offer that yet. Not for humans, not in any comparable way. Venus has scientific importance, possible atmospheric platform concepts, and a very strong case for more missions, but it does not yet have the equivalent ladder for people. It does not have the same build-up of precursor systems. It does not have the same tested operational chain. It does not have the same clear route from mission to mission toward eventual human use. So if your question is practical and immediate, Mars stays in front. But that is only one question. If the question is which planet could hit planetary science harder in the next decade, the answer may be Venus. That is the line that matters most in this whole debate. Venus can hit multiple major frontiers at the same time: active volcanism, climate catastrophe, early water history, tectonic behavior without Earth-like plate tectonics, atmospheric evolution, rocky exoplanet interpretation. That is a very unusual concentration of unanswered science in one place. Mars is still producing major discoveries, and it will keep doing that. But much of Mars' big framing is already stable. It looks like a once wetter world that lost much of its atmosphere, cooled down, dried out, and preserved accessible records of that history. Venus is different. Venus still has the power to change the frame itself. It still has the power to force textbook-level updates. If the upcoming missions show that Venus was once more temperate, that it stayed geologically active in ways we did not fully expect, that it loses heat through mechanisms we do not yet understand well, or that its atmosphere preserves a more complicated history of water and climate transition, then Venus does not just add detail. It changes the overall story of how Earth-sized planets evolve. That is why the conclusion should not be Venus instead of Mars. That is too simple, and it misses the real point. The smarter answer is Venus in addition to Mars, but for different reasons and for different civilizational purposes. Mars is the proving ground for long-duration human exploration and off-world engineering that has to keep working day after day. It is where you test whether humans can operate on another planet with local resources, surface mobility, and real infrastructure build-up. Venus is the proving ground for something else. Venus tests whether we actually understand rocky planets, climate stability, and the boundary between Earth-like and uninhabitable. That is the split. Mars tests our machines in a way that points toward eventual human presence. Venus tests our theories in a way that points toward understanding worlds themselves. And that matters because those are not minor differences in emphasis. They lead to different futures. A Mars-centered future is about expansion, operations, endurance, logistics, and eventually maybe presence. A Venus-centered science push is about understanding why some worlds remain stable and others do not. Why one Earth-sized planet stays livable and another becomes crushing and superheated. Why a rocky world can look promising in its basic properties and still end up catastrophically different. So the real answer to the title is not that Mars was the wrong choice. Mars is still the place humanity is most likely to reach first with people, because it is the one planet where the engineering ladder exists in recognizable form. The real correction is that Venus may be the planet we have underestimated the most. Mars is where you might try to live. Venus is where you learn why living worlds survive at all. That is the deeper conclusion. Mars asks whether humans can adapt to another planet. Venus asks whether planets themselves can remain stable enough for life to matter in the first place. Mars is a question about us. Venus is a question about worlds. Mars asks how far engineering can go. Venus asks how fragile habitability may actually be. And once you see it that way, Venus stops looking like a backup destination or a side topic. It starts looking like one of the most important reference planets we have. Because if you want to know whether Earth-like worlds are common or rare, stable or fragile, easy to keep habitable or easy to lose, Venus may be the harder teacher, and therefore the more valuable one. That is why this debate matters beyond simple destination ranking. It is really about what kind of future you think space exploration is supposed to serve. If the future is mainly about getting humans outward as fast as possible, Mars keeps its lead. If the future is also about understanding which worlds can stay alive and which ones fail, Venus becomes impossible to push aside. It becomes part of the core mission, not an optional extra. And that is why the clean verdict is this. Go to Mars because that is where humans are most likely to become operational first. Go to Venus because it may tell you something even more important. It may tell you whether worlds like Earth stay kind by default, or only by a narrow and fragile set of conditions that can break. And if the answer is the second one, then Venus is not just another planet we should visit. It is one of the main places where the future of planetary science gets decided. Mars is still the place humanity is most likely to reach first, but Venus may be the planet that tells you whether worlds like Earth were ever safe to begin with. And if that is true, then going to Venus is not a detour from the future. It is a confrontation with it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.